Okay. Consider this example of a Max Heap. This is a Max Heap. Max Heap is a complete binary tree, so every node should have at most 2 children. In this tree, any node has exactly 2 children, except in the lowest level. In the lowest level, we may have it is possible that we do not have some nodes. For example, here a node with a value of 7 just have 1 child, and node of value 9 and node of value 3 does not have any children. So a Max Heap is the Max Heap should be full, or it is allowed that in the last or in the lowest level of the tree we do not have some nodes. I mean, we may have these nodes that I draw in red, or we may do not have them. Here we do not have these nodes. So Max Heap is a complete binary tree, and you should have and every node should have exactly 2 children, or in the lowest level some leaves can be omitted, and some of the nodes may have less than 2 children. Here node with the value of 7 has 1 children. The node of value 9 does not have any children, and also the node of value 3. Okay. If we want to store this data structure in memory, we have 2 choices. We can implement this data structure by pointers, something like this. For example, we may define we may define each node as a record that has a value and 2 pointer for its left and right children. So if you want to implement this tree, we can use this data structure. We can implement it in this manner, that every node of the tree be a record with 3 fields. One field is the key or the value of the node, and 2 fields are left and right, or two pointers to left and right children, and so on. The children itself has 2 pointer to their left and right children, and so on. This is one way for implementation of Max Heap or Min Heap. But there is another choice. We can implement a Max Heap in an array, as we draw here. We can put the elements of the Max Heap in an array. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 nodes are in the tree. So we need at least 10 rooms in the array. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and so on. Okay, we may have an array, for example. Its name is A, and this 1 and this 2, the room, and this 3, 4, 5, 6, 7, 8, 9, 10, 11, and so on. If you are going to implement this Max Heap in an array, from top to bottom and from left to right, we put the elements of the heap in the array from top to bottom, from left to right. So the first element is the root of the tree with the value of 16. We put the root in the first room of the array. Then we come down, and in the next level we have 2 nodes with the values 14 and 10. From left to right we put them in the array 14, 10. Then we come down to the third level. In the third level, from left to right we have 8, 7, 9, and 3. We put them in the array 8, 7, 9, 3. And in the next level we have 2, 4, 1. 2, 4, 1. Okay, we have 10 elements in the Max Heap, and we put them from top to bottom, from left to right, in order in the array from the first room of the array. Okay. One question here is what's the how we can find the relation between parents and their children. If we put them in an array, we do not have any pointer that point parents to their children. In the previous approach for implementation, we have pointers that point a parent to its children, but in the array we do not have pointers. So how we can specify what node is the parent of what node and what node is the children of what node. This is done by a relation between the indices of the parents and children. Okay. Okay. In the previous approach that we draw it in the top of the slide, we implement Max Heap by pointers. We have records that have 3 fields, 1 field for the value of the node, and 2 fields are left and right pointers to the left and right children. So by these pointers we know what node is we can find what nodes are children of what parent node. We can follow these pointers and find the children of a node. But in the array, we do not have pointers that we can use to follow and find the children of a node. So we should define another way for finding the children of a parent node or the parent of the children. We do this by defining a relation between indices in the array. Let me show it on the picture of Max Heap. The root is in index 1. Okay, in the first room of the array, the root is placed in the first room of the array, so its index is 1. The node with value 14 here in the room of index 2. The node with the value of 10 has index 3 in the array, and so on. Index 4, 5, 6, 7, index 8, 9, 10. The numbers that I wrote beside each node is its index in the array. Okay, the root has index 1. Its children has index 2 and 3. So there is a relation between index of a parent and its children. Left child of a node which is in index I is placed in the room with index 2i, and right child of a node with index I in the array is placed in index 2i plus 1. And parent of a children with index I is placed in a room with index I divided by 2 we give its floor, the floor of this division. Let me check it in the example. In our example, node with value 16, which is the root, is in index 1. Its children is placed in 2 multiplied by 1 and 2 multiplied by 1 plus 1. Please let me write it. Left child of 1 is in 2 multiplied by 1 is 2. Its right children, its right child is 2 multiplied by 1 plus 1, which is 3. So the children of the node which is in room of index 1 are in index 2 and 3. In this picture, the children of the node with the value of 14, which has index 2, are in index 4 and 5, which is 2 multiplied by 2 and 2 multiplied by 2 plus 1. Children of 2 is placed in 4 and 5 places in the array. Left child of the node which is placed in index 2 is in index 2 multiplied by 2, and its right children, its right child of 2 is in 2 multiplied by 2 plus 1, which is 5. So the formula is what I wrote in the top of the slide. Okay, any question? So by these formulas, we can find which room of the array is the parent of which room, and which room is the children of which room. Oh, okay, about the parent. For example, in the picture, the node with the value of 8, which has index 4, and the node with the value of 7, which has index 5. We should divide the index of the node by 2. 4 is divided by 2 is equal to 2. And 5 divided by 2 is equal to 0.5, which we get its floor, which is 2. Okay. Here, parent of 4 is index 4 divided by 2. That we get its floor, which is 2. Parent of the node which is in index 5 is 5 divided by 2, its floor. By floor we mean we get the integer part of a float number. 5 divided by 2 is equal to 2.5, and its floor is 2. So to find a parent of a node, we can divide the index of the node and get its floor, and then we have the index of its parent. Okay. So we can implement a Max Heap in an array, and we by these formulas we can find which node is the parent of which node and which node is the child of which node. Okay. Any question? For both of them, you can use this manner both for Min Heaps and for Max Heaps. The only thing that differs is in Min Heap the value of parent is less than or equal to the value of its children, but in Max Heap the value of parent is greater than or equal to the values of its children. The other things are the same. This formula also works for Min Heap and anything else. Okay.
Please, doctor, could you repeat that example again?
Another example?
No, this one, just the next step. So this one, I mean, the root, the head, it's 16. The index for 16, it's 1, right?
Okay. Okay.
So how we can find the root? It's 16 divided by 2, right?
No, 16. No, 16. Its index should be multiplied by 2. Its index is 1 is multiplied by 2.
Mm-hmm.
We multiply its index, not the value. We do not use values. we use index. Its index is multiplied by 2, and its index is multiplied by 2 plus 1 gives us the index of the left child and the index of the right child. Sorry.
Appreciate it, Doctor. Thank you.
Okay. Is it clear?
Yeah, it's clear now. Thank
okay.
you so much.
For example, consider the node with the value of 10. Its index is 3. The index of its children is 3 multiplied by 2, which is 6, and 3 multiplied by 2 plus 1, which is 6 plus 1, which is equal to 7. So the indexes of the left and right child of the node with the value of 10 with the index 3 are in indexes 6 and 7, and so on. We can easily find which node, which room in the array is the parent of which room, and which room is the child of which room. We do not need pointers here. We can use these indexes and this formula to find the parental relationship between the nodes in the array. Okay, let's continue. In the following, we are going to explain how we can make a heap, how we can build a max heap. If we have some numbers, we have some data, and we are going to make a max heap by them, how we can do this task. There is a question: is it possible to get the slide for this lecture and previous lecture? The lecture is okay. Oh, sorry, I forgot to record the lecture. Usually yes, every lecture is recorded. Every lecture is recorded in the system, and if you have access to the system, you can play the previous lectures which are recorded in the system. So don't worry about recording of the lecture. And it is also recorded in Google Meet, as your friend do it. So there is no there's no problem about recording the sessions. They are available. Okay. The content of the lectures also is in the book. You can read the book, and it has a simple text. You can easily read it and follow the content of the lecture. Okay, let me continue. We are going to describe how we can make a max heap, build a max heap. Okay. Sol, any question? Okay. Suppose we have an array with some numbers in it, and we are going to make it a max heap. We are going to convert it to a max heap. For example, I draw it in a tree. Suppose the first node has value 1. Three, 5, 2, 4, and 6. If we consider we have this tree, this tree is not a Max Heap. We are going to build it. We are going to convert it to a Max Heap. So the title of the discussion is building a Max Heap. If we put the values of this tree in the array, we should put the value 1 in the first place, then 3, then 5 from top to bottom, and from left to right. Then 2, 4, and 6, and this 1, and this 2, 3, 4, 5, 6. We put the elements from top to bottom, and in each level from left to right. So the first element, the root, is placed in the first room, then in the next level 3, 5, and the third level 2, 4, and 6. Okay, this is not a Max Heap, because in Max Heap the value of each node should be greater than or equal to the value of its children, but here 1 is not greater than 3 or 5, and 5 is not greater than 6, 3 is not greater than 4, so it is not a Max Heap. How we can convert this tree to a Max Heap? Before we explain how we can build a Max Heap, we are going to introduce an auxiliary function which helps us to making a Max Heap. We use an auxiliary function, a function that gives a tree whose left subtree and whose right subtree are already a Max Heap, but the whole tree is not a Max Heap. We use an auxiliary. I'm not sure about the spell auxiliary function. We name it Max Heapify. Max Heapify is a function which gives as input a tree whose left subtree and whose right subtree are Max Heap, but the whole tree is not a Max Heap. So we give this tree as input, and we are going to convert it to a Max Heap. The only problem in this tree is that its root may be not greater than or equal to its children. For example, here we may have in the root 1, and in its children, for example, 8 and 6. Okay, if you have such a tree that its root has value 1, and the value of the root of its left subtree is 8, and the value of the root of its right subtree is 6. And the left subtree is a Max Heap. The right subtree is a Max Heap. There are some nodes below these nodes. There are some. Suppose there are some nodes in left subtree, and there are some nodes in right subtree. And left and right subtrees are Max Heap. We have only one problem in this tree, which is that the value of its root is not greater than the values of its children. We can solve the problem by comparing these three values and put the maximum in the root, or swap the value of the maximum and the value of the root. For example, here the value 1, 8, and 6. The maximum of these three values is 8. 1, 8, 6. The maximum is 8. We can swap the value 8 and the value 1, the value of the root and the value of the node that has the maximum value. So we swap them. We swap 8 and 1, and this tree is converted to a tree that its root has value 8, the value of the left subtree, the value of the root of the left subtree is 1, and the value of the root of the right subtree is 6. Okay, now the problem between the root and its children is solved, and the value of the root is greater than or equal to the value of its children, but because we changed the value of the root of the left subtree, we may have problem in the left subtree, because the root of the left subtree now may not be greater than or equal to its children. So we recursively should solve the problem in the left subtree. The problem moves from the root of the tree to the root of the left subtree. Okay, so we can recursively do the same thing for the root of the left subtree. Okay, let we do this scenario and the given tree, and the given example tree. Okay. Let me run this the scenario in an example. Suppose we have this tree. 1, 8, 6, 5, 3, 4, and 2. Okay, here the left subtree is a Max Heap. Okay, Max Heap. Left subtree, left subtree. The right subtree is also a Max Heap. right subtree is Max Heap. So we have a tree that its left subtree is Max Heap, its right subtree is Max Heap, but the total tree is not a Max Heap because the value of root is 1, but the value of its children is 8 and 6, and the value of the parent is not greater than the value of its children. So we use a function maxify to solve the problem and converting this tree to a heap. At first, we compare the values of the root and its children between 1, 8, and 6. We find the maximum is 8. We swap the value, the maximum value and the value of the root. The maximum value is 8 and the value of root is 1. We swap these two values. So the tree is converted to this tree as we draw here. The value 8 is moved to root. Right subtree does not change. Does not change. But the root of the left subtree is no 1. The value of the root is no 1. Okay, در واقع after swapping 1 and 8, we have this tree. Okay, now the problem is solved at the top level because now the value of root is 8, which is greater than the value of the values of its children. But because the root of the left subtree is changed, maybe a problem in the left subtree. So we do the same thing recursively in the left subtree. So for the left subtree, we again compare the value of the root and the values of its children. The value of root is 1. The value of its children is 5 and 3. So we find the maximum. The maximum between these three values is 5. Then we swap the maximum value and the value of the root of the subtree. So here 5 and 1 is swapped and we get this tree. The tree is converted to this one. The right subtree does not change. In the left subtree, value 5 is placed in the root and value 1 is placed in the children. The value of the maximum value and the root value are swapped. No, the problem is solved in left subtree. But because the root of this subtree, I mean, this tree may also node 5 here may also have children, and we may have also problem in the subtrees that are below than node 5. But here, because we do not have any children, and the node 5 in the previous tree was a leaf, the problem is solved totally, and do not need continue, and the problem is solved and the process is finished. After swapping 1 and 5, we get this tree. Okay, so please check the questions.
Sorry, doctor, I have a question.
Okay, please.
What about the index? When we put the index before rearrange the tree as a max heap or after? Because when we arrange the tree, the index will rearrange someone.
Indices are fixed in the array. We do not change indices. Here, for example, here, index 1 is for root, index 2, index 3, index 4, index 5, index 6, and index 7. In this tree, also, we have index 1, index 2, index 3, index 4, 5, 6, and 7, and here index 1, 2, 3, 4, 5, 6, and 7. So the index is related to the position of the node. We just swap the values. The values.
That's clear. You mean we put value in the index, change the value in the index.
We swap the values in the index. Yes.
Okay, thanks.
Okay. Okay. One question is about exercise. We put exercise. We define exercise for you. Then you try to solve the exercise. After that, we give you the solution and explain how the solution can be obtained, how the solution can be get. So after giving you the exercise, we do that. Okay. 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 The rest, okay.
ببخشید دکتر صدام دارید؟
بله please لطفاً one by one, please one by one so that do not
دكتور I'm
with each other.
raised hand but you down it.
Okay.
Sorry دكتور, I have one question. At the first step, at the original tree, if we suppose the node that have index 4, if its value 10, okay?
Let me return back.
Doctor, sorry, the last slide. The last slide.
The last slide. Okay. The last slide.
Yes, the original tree, the first one,
tree.
the first step. If we suppose the node that have index 4, if it's value 10, if it's value 10.
Here we have value 5.
Okay.
It's another.
If we suppose that it's value 10.
Okay.
So
suppose it as value.
So we can. So we can swapping the rows multiple.
Okay, so let's suppose it has value 10. Okay.
Okay.
Okay. or assumption is that the left subtree is Max Heap, is itself a Max Heap. If the index with the index of 4 has value 10, it is not a Max Heap because 10 is greater than 8. Okay, we assume that the left subtree is Max Heap itself. Our input is a tree, its left subtree and its right subtree are already Max Heap. We are going to make the total tree a Max Heap. Okay, it's an auxiliary task, not the main task. We are going to solve this problem first, then we are going to make an arbitrary tree with any values to a Max Heap. Okay. In the first task, we assume that the left subtree and the right subtree is our Max Heap, already Max Heap. Okay.
اوكي دكتور ممنون خیلی واضح بود.
Okay. Okay. Okay, so we describe in this example how Max Heap works. Okay, Max Heap is an auxiliary function which we use. The input of this function is a tree whose left subtree is already a Max Heap and its right subtree is also already a Max Heap, but the whole tree, the total tree, is not a Max Heap. We are going to convert it to a Max Heap. We do in the manner that I described before. First, we compare the value of the root and its the values of its children, and find the maximum and swap the maximum with the value of the root. Then the problem goes down to the left subtree. To the left subtree, we do the same. Again, we find the maximum of the root of the subtree and its children, and swap the maximum with the root of the subtree, and go down until we reach to a leaf. In the leaf, the problem is solved and we do not need to do anything else. In this manner, we convert a tree, the given input tree, to a Max. In the following, we are going to describe how an arbitrary tree can be converted to a Max. Any question? Okay. Yes, yes. We may have the same problem in the right side, but note that only one of the sub trees may have the problem, because we only change one root of the subtrees. In the first step, when we find the maximum may be root itself. Again, if the maximum is root itself, we do not have any problem, and the given input tree is already a Max Heap. If the maximum is the root of the left subtree, the problem goes to the left subtree. If the maximum is the root of the right subtree, then the problem goes to the right subtree. So we need only consider one subtree. We do not have problems with both subtree. We move the problem to left subtree or to the right subtree, only one of them. Okay, and if the problem goes to any subtree, we do the same as I described. Here, the left subtree is a Max Heap because 5 is greater than 3 and 4. The right subtree is also a Max Heap because 8 is greater than 7 and 6. But the whole tree is not a Max Heap because 2 is not greater than 5 and 8. So at the first step, between the value of the root, which is 2, and the values of its children, which are 5 and 8, we find the maximum. Maximum is 8. 8 is swapped by 2, so the root will be 8. The left subtree does not change, so we do not have problem in the left subtree. The left subtree before was a Max Heap, and now is also a Max Heap. We do not change the left subtree, so the problem is not in the left subtree. But the root of the right subtree is changed. It is 2 now, and its children is 7 and 6. So the problem moves to the right subtree, and we should solve the problem of the right subtree. We do the same as we did before. Again, we find maximum between 2, 7, and 6, and swap the maximum with the root. So in the next step, the root of the right subtree is swapped with its children. 7 goes to the root of the right subtree, and 2 goes down. The right subtree, the left subtree does not change, so it is Max Heap as before. Now we reach to a leaf. The value we have a leaf with the value of 2, and this leaf does not have any children, so we do not need to do anything else. And finally, we have a Max Heap here. Okay. In each step, we just swap 2 values, parent and one of its children. Okay, we do not swap more than 2 values. We just swap 2 values with each other. We find the maximum between parent and its left and its right children. After finding the maximum, we swap the maximum with the root. Okay, the root should be maximum, and we swap the maximum with the root. Three cases are possible. When we find the maximum between root and its left and right children, the maximum may be root itself. If the maximum be the root itself, so there is no problem, and the given input tree is already a Max Heap, and you are done. But maximum may be the root of the left subtree or the root of the right subtree. If the maximum is one of the root of the subtree, we swap the root of the subtree with its parent value, and the problem goes down to that subtree, and we continue in that subtree. Here we suppose that we do not have problem in the left and right subtree at the beginning, and the input tree, its left subtree and right subtree are already Max Heap, and we are going to solve the problem of the root of the tree. But in general, when we are given a tree, it may be arbitrary. It may have arbitrary values, and left subtree or right subtree may not be a Max Heap, and we should convert first. We should first convert their subtree to a Max Heap, and then use this auxiliary function to convert the whole tree to a Max. Please continue. We are going to in the next.
Sorry, Doctor.
Okay, please.
Can I ask two questions?
Yes, please.
If we can back to the last example.
Okay.
Okay. If we have the two subtrees have parent 8, so replace the 5 number with 8, the second index. Which subtrees will take first?
If in this example, instead, if in this example we have in the left subtree 8 and in the right subtree 5, we should find the maximum. In this example, the maximum is in the right subtree. In the previous example, as you see, the maximum was in the left subtree. So we find the maximum may be in the left, as in this example, and we swap the left subtree with root. And
sorry, Doctor, the left and the right is 8.
Both is 8. Okay.
Yes, the both.
Oh,
the both
okay.
is 8. What will I take first, the right or the left, or it's not matter?
Okay. If both left and right are the same, it does not matter which one we select. Okay.
Okay. Did there is a code to write it, or just draw the update?
Let's have an example such that, for example, assume both left and right have 8 values. Here we have choice to select which one. You can select left child or right child to swap. Okay. For example, in this tree, you can choose the left child or the right child for swap.
Yes.
It does not matter. You have choice. Okay. For example, if we select left, then we have 8 in the root, and we have the value of root in the root of the left subtree. Then we should solve the problem in the left subtree. But if we choose the right subtree at the first, the problem goes to the right subtree, and we should solve the problem of the right subtree. Both of them is okay. Here in the left subtree, we should again find the maximum. Maximum is 5. 5 goes to the root of the left subtree, and 2 goes down. We can do the same for the right subtree. No, it does not matter, and both of them is okay.
Is this the solution, or I should write a code with this solution to sweep between the node?
I do not. I cannot find your point.
Is this that's just the solution?
No, you have choice. You can. It's one solution for every problem may have maybe more than one solution. It's one of the solutions. Here you have choice. You can choose the left one or the right one. Also, there are other solutions that we do not discuss them here. It's just a solution for any problem. We may have many solutions. It is just one solution.
Thank you, Doctor.
Okay.
بخشید میتونم صحبت کنم؟
بله بفرمایید.
دکتر همون previous slide.
Okay.
If you can previous, not this.
Previous one. Okay.
Okay. Doctor, my friend, he said if we swapping the subtrees, the root of subtree left, if this root we swapping with the root of right subtree. In this case, not Max Heap, the right subtree. Okay.
Yes. Okay. You are right.
Oh. حالا نمیتونم بذار فارسی صحبت کنم. میشه باش. اون وقت اگر مثلا اینو عوض کنیم مثلا 5 همون 5 با اون شماره 8
عوض کنیم دیگه مکس هیپ نیست سمت راست درسته.
این اون وقت ما میگیم یعنی we can't say this Max Heap and the solution. یعنی فارسی رابطه من نمیتونم فارسی صحبت کنم که بچه‌ها شاید هم متوجه نمیشن.
مشکل نیست، من دوباره انگلیسی توضیح میدم. بگو.
باش. دکتر اگر ما عوض کردیم خب اون وقت میشه ماکس هیپ نی. خب وقتی میخوام پاسخ بدیم میگیم مثلا این ماکس هیپ نیست یا باید این هم دوباره عوض کنیم اون نود لیف نمبر 7 باید.
ببین ما ورودیمون باید حتما چپ و راستش هیپ باشه، اگه نباشه اصلا اینو اصلا قبول نمی‌کنیم. مثلا باید بگیم
یعنی کلا پاسخ ماست کلا دیگه میگیم ماکس هیپ نمیشه کلا. درسته؟
yes. برای فانکشن maxipify فرض اینه اصلا این maxipify function we suppose that left and right subtrees are already max heap. So if the left subtree or the right subtree is not a max heap, then maxipify function does not work. So for maxipify function we must have a tree, we must given a tree as input to this function that both subtrees are max heap. Okay. In the following we talk about arbitrary trees that we are talking about arbitrary trees, and we are talking about how we can convert an arbitrary tree to a max heap. Okay. But at the moment, we suppose left and subtrees are already max heap. Okay.
Okay, doctor. Doctor, the second question. Also, my friend, he said in the exam only we construct the trees, or you want code, writing code.
Okay, don't worry about code. We do not ask you to write codes. Okay.
So only we construct subtrees.
I give you some examples and ask you to convert this tree step by step to a Max Heap. So I do not ask you to write codes. Okay, don't worry about code.
Okay, that's good. Merci, Doctor.
Okay. Don't worry about code. Okay, now let's to describe how we can convert an arbitrary tree to a heap. We have an arbitrary tree. Okay, here we do not suppose that left subtree and right subtree is are Max Heap. How excuse me, how we can convert an arbitrary tree to a Max Heap. Okay, suppose we have an arbitrary tree. Consider an example. For example, this tree. 1, 8, 2, 7, 3, 5, 4. Okay. In this tree, the left subtree is a Max Heap, but the right subtree is not a Max Heap, and the total tree is not a Max Heap. We are going to convert this tree to a Max Heap. One of the students has a question. What is the method of asking a question in an exam? Can I have one example? Yes, I told you. We give you some examples and ask you to run some algorithms on this example. I will give you some sample, and also you have some exercises. I define for you some exercises that you should solve them, and in exam questions are similar to exercises that I give you. Okay, so the following you are going to be familiar with the questions, and you will know how the questions will be in the exam. Okay, don't worry about the exam. Describe how we can convert this tree to this arbitrary tree to a Max Heap. If you see the leaves, I mean the nodes that have no children, a node that has no children in the tree is called leaf. Any leaf as a single subtree is already a Max Heap. I mean, node with the value 7 is a Max Heap itself. Node 3 is itself a Max Heap. Node 5 is a Max Heap. Node 4 is a Max Heap, because these nodes do not have any children. So any leaf is a Max Heap. Okay. If we come one level up from leaves at the one level upper than leaves, we have a subtree. We have subtrees whose children are Max Heap. I mean, in this subtree, the subtree whose root is node with value 8, we have a subtree whose left and right is Max Heap, because node with the value of 7 is a Max Heap, and node with the value of 3 is a Max Heap. So the subtree that are shown by red circle is a tree whose left and right subtrees are Max Heap. So we can use the previous function, the function maxify, the previous auxiliary function maxify for this tree to convert it to a Max Heap, because the conditions of the input is satisfied. We have a tree, we have a subtree here whose left and child subtrees are already Max Heap. So we can call maxify here, Max Heapify. Also for the left subtree, in the left subtree, again we have a tree whose left and right subtrees are already Max Heap, and we can call auxiliary function maxify here. Okay. If we call maxify, the previous function that we discussed, for these two subtrees, they are converted into Max Heaps. Okay. So after calling maxify for these two subtrees, we have a new tree. Let me draw it. 1, 8, 7, 3, 5, 2, 4. If we call maxify for the left subtree, nothing happens, because the maximum value between 8, 7, and 3 is 8, and it is the maximum value is for the root. So the subtree already is a Max Heap, and the function is, we find the maximum between 2, 5, and 4, and maximum is 5. Then we swap the maximum with the root. 5 is swapped with 2, and we get the 3 in the right. So after calling maxify for the left subtree and the right subtree, we have this 3 in the right side. Okay. Now we come one level up, and because already this tree left and right subtrees of this tree is or Max Heap. Now we can call maxify for the root, because we previously converted its subtrees to Max Heap. Now we can call maxify for the root. So we call maxify for the root, and as we described before, if we call maxify for the root, this function finds maximum between 1, 8, and 5. Maximum here is 8. 8 is swapped with 1, and 1 goes down. So
Excuse me, doctor.
Okay, please.
So it doesn't matter. I will change which one first, the subtree or the main tree, right? So I have to get the final solution.
Okay, it's important. We should start from below to top, from lower levels of the tree to top. We should start first from one level upper than leaves, and then one level upper than it, and so on. We should start from bottom to up. We should first, please let me show it in the next slide. If we have a tree like this, leaves are already Max Heap, so we should start from one level upper than leaves. If we should call Maxify first for these 4 nodes. Okay. After calling Maxify for any of these 4 nodes, then we can go one level upper and call Maxify for these 2 nodes, and after that we go one level upper and call Maxify for roots. So we should start from bottom to up, because when we call Maxify for a node, Maxify suppose that its children are already Max Heap, so we should start from below to top, from lower to upper. Okay, it's important. We should start from one level upper than leaves, then go up to the tree.
Doctor, first
Okay,
solution down to top and to top.
Down to top. Yes. We should call Maxify first for these nodes, then for these nodes, and last for the root. Okay, from
The rest.
we should call Maxify from bottom to top, because when we go up, its subtree should be converted to Max Heap before. Okay, because Max Heap, I suppose the subtree of the input tree are already Max Heap, so we should start from bottom to top. Okay,
so
let me
great,
write.
doctor. Thank you, doctor. Another question. May
Okay.
If we found the subtrees or subtrees, 2 subtrees, for example, if we have these right subtrees, for example, this one, can I make or solve 2 sides on the same time, one step, or I have to make step by step?
Yes, we can call Maxify in parallel for any nodes that are in one level. Okay, because these are independent from each other. For example, here, if we have node A, B, C, and D, we can call Maxify for node A, B, C, and D at the same time, because these subtrees are independent from each other. But we should call Maxify for all of them. Then we go one level up. Okay.
Okay, many thanks.
There is no order. There is no order for calling Maxify for the nodes in the same level, but there is an order between levels. We should call Maxify for lower levels, then go to the upper levels. Okay.
Thank you so much. I appreciate that, Doctor.
Okay. Let me write the codes of the Maxify and the codes of build a Max Heap. These codes help you to understand the algorithm better. Okay. Max Heapify. I first write the code of Max Heapify. This function gives two inputs. The first input is array, the array that we store the values in it. It's the input array. I describe you how we can store a Max Heap in an array, so we can give the tree to Maxify function in an array. Okay, A is the array that the tree is stored in it, and I is the index of the root. Index of the input tree is the index of the root of the input tree. Okay, root of the input tree. First, we compute the index of its left children. L equals to left child I to R equals to index of the right child I. First, we compute the index of the left and the right child of the root. Then we should, in Maxify, we should find the maximum, okay? The maximum between root and left and right. First, we compare root and the left child. If L is less than equal to heap size A, and AL is greater than AI, then okay. Here first we compare the index of the left child L with the heap size. What is the heap size? Heap size is the number of elements of the heap. Okay, the number of elements of the heap. How many values are in the heap? How many nodes? Heap size is the size of the heap. So we compare in the index of the left child to the heap size. Why we do this comparison? Because we should show that node I has left child. If this L, which is the andis of the left child, is greater than heap size, this means that node I does not have left child. Okay. Let me go back Here in the first slide, node with the value 9, which has index 6, if has any children, their children should be in 6 multiplied by 2, which is 12, and 6 multiplied by 2 plus 1, which is 13. But we do not have 12, index 12 in the array. Okay, the size of the heap is 10 here. Heap size is 10. The number of nodes of the tree is 10. So if an index if an index is greater than heap size, this means that that index is not valid and that node does not exist in the tree. Okay, so before any comparison, before any finding maximum, we should sure that that node already exists. Should sure that the node exists in the tree. Okay. For that, we compare here. We compare here the index of the left child with the heap size. The index of the left child should be less than or equal to the heap size, and then we compare the value of the left child and the value of the root. A L is the value of the left child. A I is the value of the root. We check here that if the value of the left child is greater than the value of root. If it is if this is true, then the maximum of left child and root is the left child. Okay, so we have a variable named largest. We set largest to L because largest of the root and the left is the left. Okay, but if the condition does not satisfy, in the else case, largest will be I. Largest will be the root itself. Then we compare the largest with the right child. We check. Okay.
You know, the voice, it's just left. It's just gone. Sorry. So could you please repeat these steps?
Here we are going to find the maximum between left child, right child, and I. Okay, I is the root. Okay, I is index of the root. The index of the left. We first compute the index of the left child, the index of the right child. Then we check the values. We compare the values. First, we check if the left children there exists. If L, we check if L is less than or equal to heap size. This is for ensuring that the left children there exist. A node may do not have children. Okay, if the index of the left child is greater than heap size, this means that the left children does not exist. Okay, so we show here that the left children that exist, and then we compare its value to the value of its parent. We compare AL and AI. A is the array. AL is the value of the room of the array with the index L. Okay, it's the value of left child. AL is the value of left child. AI is the value of the root. Okay, If the value of left child is greater than the value of root, then the maximum is left child. We set largest to L. Otherwise, we set largest to I. I is the maximum. Then we compare the maximum of the left and the maximum of the left and root with the right child. We compare it with right child, the value of right child. So we check if the right child there exists. If R, index of the right child, is less than or equal to heap size, this means the right child there exists. Then we compare the value of the right child, AR is the value of the right child. We compare it with the value of the maximum of the left and root, which is A largest. Then if this condition satisfy, this means that the value of right child is greater than the value of left and root. So we set largest to R. Largest is set to R. Okay, until this step we compute. We computed the maximum. Which one is the maximum? Left, right, or the root? Largest variable, largest contains.
Can we ask questions,
Contains
Doctor?
the maximum, the index of the maximum value. Yes, please.
In step 6, why write A of largest, not A of I?
Because before we compare AI and AL and find which one is the largest, then we compare R with the largest one. Okay. Yes, I know. And we find which one is maximum. Okay. We find which one of the left or root is it, which if the largest is I itself or not. Okay. If the largest is I, this means that its root value is the maximum. Okay, so we should give as input to maxify array A, but the index of root is now the index of the maximum, which is largest. So we give as input the largest to the maxify. Largest is the index of the subtree that has the maximum value in its root. Okay, this code this code is a formal specification of what we did in the previous examples. As I explained for you on examples, this code describe that action formally. We can see what we are doing in Max Heap formally. This code works on array. Okay, here we have an array. We do not have pointer. As you see, left child and right child are the we at first we find the maximum between these three index. We compare the value of these three index because we store them in an array. We have something like this. Index I is the root, 2i which is L, and 2i plus 1 which is R. We compare these three values in the array L, is equal to I. R is equal to I plus 1. We compare I, A, L, and A, R to find which one is maximum. In step 1 and 2, we compute the index L and R. L is 2I, R is 2I plus 1. In step 3, we compare the value of the AI and AL, the value of root and the value of left child. If the left child is greater than root, largest set to L. Otherwise, largest set to I. So largest is the index of the maximum value between left and I, between left children, between left child and the root. Then in step 6, we compare the value of AR, the value of right children, the right child, with the value of the largest. Largest here may be root or maybe left child, any one that has the greater value. So we compare the value of the right child with the value of the maximum. Okay, if the value of right child is greater than the value of the maximum of left and root. In step 3, first we compare left and root and find the maximum of the left and root. In step 6, we compare the value of the right child with the previous maximum to find which one is the maximum of 3 values. After we find the maximum and the index of the maximum, largest is the index of the maximum. A largest is the value of the maximum. In step 8, we check if the maximum of I, L, and R, if the maximum of AI, AL, and AR is AI, this means that the maximum is already the root. So we do not need to do anything else because the root is maximum of the 3 values and is greater than left and right. So we already have a Max Heap. So we do not need to do anything else. We can return from the function. But if the largest is not equal to I, this means that the largest may be the value of the left child or the value of the right child. In this case, we need to swap the value of the left child or right child with the root that we do here in step 9. We swap the value of the maximum or a largest. A largest is the maximum value, which may be the value of the left child or the value of the right child. We swap it with the root. Then we should in step 10 we should go to the subtree. We should go to the subtree and call the function recursively for that subtree. Which subtree? The subtree that has the maximum value in its root. So its index is identified, is specified by largest. Largest is the index of the maximum. So we call maxify for that subtree whose index, whose root index is largest. Okay.
So that's mean if the largest
is I, L, or R, any of 3 whose value is maximum. If the value of AI is maximum, largest is I. If the value of AL is maximum, largest is L. If the value of AR is maximum, largest is R.
Salam, Doctor.
Salam alaikum.
Doctor, in the step number 8, we can write if A of largest not equal A of I. I mean, we compare between values, not between index. It's possible.
Two values A largest و A I. Yes, it's the same. It's the same because both of them is correct. Yes. Both of them are correct. In step 8, we are going to check the maximum value is not the root. If the maximum value is root, then there is nothing to do. We can return from the function. But if the maximum value is not the root, we should swap the maximum value with the value of the root and continue in that subtree. So here we can write also if A largest not equal to A. Okay.
Doctor. If the largest is equal I,
Okay.
then jump to step 10.
We jump to step 11. I mean we exit from the function. Okay.
Okay.
These two statements, step 9
if not equal,
is under step 8 is inside the if statement. If the if statement does not satisfy, then we go to step 11, which is the end of the function, and we return back.
Thank you, Doctor.
Okay. Any question? Largest is not the big value. Largest is the index of the big value. Okay. One question is that I repeat. You mean I explain step 8 of the algorithm, or I explain slide 8? I do not give your point. I didn't give your point. Okay. Is there any question?
No.
Please let me finish the lecture. What I said until now is the code of the Max Heap file, which gives as input a tree whose left and right subtrees are Max Heap file, and convert it to a Max Heap. I explained how an arbitrary tree can be converted to a Max Heap. I said that we should start from lowest level and go up, and in each step we should call Max Heap as I described in slide 7 and slide 8. Please write its code. Its code is short. Is a short code. I write it here, and we finish the lecture. build Max Heap. It's a function that gives an array, an arbitrary array. An arbitrary array. And convert it to a heap. Step 1, for I from heap size A divided by 2, then its floor down to 1, 2. Max EPFI A and I. This is the code, the short code. As you see, we just call Max EPFI for some nodes. For which nodes? For nodes with index which is a heap size divided by 2 down to 1. 1 is the index of the root. If I draw an example, if we have if you have a complete binary tree, you have a complete binary tree which is full, the number of leaves is approximately half the total number of the tree. I mean, if n is the number n is the number of nodes, the number of leaves is n divided by 2. Okay, we do not need call Max EPFI for leaves, so we can start from nodes that are not leaves of the tree. Leaves are in index n, n-1, and so on until n divided by 2. The index of the root is 1. The index of the nodes that are not leaves is less than n divided by 2. So we can start from n divided by 2 down to yek and call Max EPFI for these nodes. So we call Max EPFI for nodes that have index less than n divided by 2. We do not need call Max EPFI for leaves. But if we call Max EPFI for leaves, it does work. No problem. occurs if we call maxify for leaves, but we do not need to call maxify for leaves because leaves are already heap or already a max heap, so we do not need call maxify for leaves. Because of that, we start from n divided by 2 down to 1 and call maxify for nodes of these indexes. Any question? These codes we give you these codes for your understanding, and we do not ask you to write codes in the exam. Okay, don't worry about codes, just see the code and see how the algorithm works. I just ask you in the exam to run the algorithm, on an example, and I do not ask you to write codes. Okay. You should only know how the code works. On an example. Okay. Okay. Have a nice afternoon. مساء الخير. See you later. Okay. Bye.
Thank you very much, Doctor.
خداحافظ.
Have a nice day.
خداحافظ.
خدا حافظ. خدا نگهدار.
خداحافظ.
يا حافظ دكتور. Thank you دكتور.
دكتور خدا حافظ.
You are welcome.
Thank you, Doctor.
في أمان الله.